Hey, workshop students. Let's see. I got a question here. It's actually a three-part question from week 6 quiz that you just took on Friday. And this individual was asking about number 3 and 4 and 5. And let me separate those into 3 little videos, starting with number 3. And just point out that if you haven't seen any of my other instructional videos, I like to say when you're doing Newton's 3 laws, there's 4 main steps you want to take. And if you follow these 4 steps, particularly in order of, making sure you do them completely, they make the next step real easy. If you do one of these steps not at all or poorly, it really makes it difficult. It's kind of like going up a staircase, 1, 2, 3, 4. It's easy to get to the top if you take one at a time, but if you skip one, it's a little harder. And if you try to skip 2, it's nearly impossible. And so here are the 4 steps. And so watch me as I go through these 3 problems. I will go ahead and follow these 4 steps. So the first one is to get a good physical picture of what's going on. And the second one is to translate that into a free body diagram. That kind of reduces our thinking down and gets us to focus on the object and just the forces involved. Then we write out the equations and then solve the equations. And those are kind of my recipe for my 4 steps. Watch, this one says here, a block with mass 6.08 kilograms slides down a ramp inclined at 30 degrees. All right, so maybe for starters, to get a good physical picture of what's going on, I'll put the block here, and maybe for the moment, I'll just call it mass M and angle theta. Of course, we know theta is 30 degrees, and we know the mass. This one is 6.08. Now, I know that on the quizzes, the numbers get mixed up here and there, but the logic is still the same, okay? The coefficient of kinetic friction between the block and the ramp is 0.332. All right, so what's going to happen is this is going to slide down, it looks like, and then this rubbing here in between creates some friction. So let me call that F sub S. All right, so there's that friction. Now, I'm starting to get too far and starting to label forces, which is part of the free body diagram. So let me just pause right here and say, okay, this is step 1, a good physical picture of what's going on. So it looks like all I have here is a block really on an incline. And so there's a combination of the force of gravity and the interaction of the block with the incline. So I would call that step 1. Okay, good physical picture. Now, a good physical picture should make the free body diagram a little bit easier to do. And the free body diagram should make writing out the equations a little easier to do. All right, so this free body diagram is saying forget everything else except for the object in question. All right, so I'm not going to draw the incline. I'm not going to draw anything else but the block in question. And then draw the forces. So don't draw vectors for velocity. Don't draw other things, just the forces. And you don't even have to say what kind they are because it doesn't really matter whether it's an electrical force or a frictional force or a gravitational force. It's just the sum of all those forces determine the motion. So that's the benefit of this second step here, the free body diagram. And what I like to say, especially at this level, is that you're always going to have the force of gravity pulling downward. So I like to label that one first, and then everything else touching it. So you just want to be careful here to make sure you don't miss any forces. You got to label all of them, all right? And so what is touching it is only one thing, and that's the incline itself. And so the incline we can think of as made up of components. It's really just one force, but it would be a component that's perpendicular to the surface, which we call the normal force. And just looking here at your class, I like to use the lowercase n for normal force. But sometimes there's F sub n, and sometimes there is capital N. And I don't see anything indicating one way or the other. So I'm just going to put F sub n, but it wouldn't surprise me if you're using F sub n. Okay, so there's a normal force. Now, tangential to the surface would be the friction, and the friction would be opposite of the direction it's moving. So the problem indirectly implies it is moving. Oh, there it goes, sliding down. It actually says it. Slides down the ramp. So it actually says it's moving. Okay. And so the friction would then be up the ramp. And there's step 2. I'm done with step 2, the free body diagram. So let's see. I got force of gravity and everything touching it. And the thing touching it has a perpendicular and tangential piece. The tangential piece is friction, and the perpendicular piece, the normal piece, is just that, the normal. That's why we call it the normal. Okay. So there is step 1 and step 2. Good physical picture, free body diagram. And then step 3 is probably the main thing that I could share with you and kind of help you through, is I call it write out the equations. And you're going to write out the equations based upon the picture you see in your free body diagram. I like to divide my paper in 2. I like to put an X and a Y, because when I say write out the equations, and the reason I say it's plural is because the sum of all the forces have to equal mass times acceleration. But that's a vector equation. We wrote it like this. The sum of all the forces vector equals mass times acceleration vector. And so the point is that it has 2 pieces. It has an X and a Y component. Okay. And so then you start to write out the equation. Now, I will say that part of writing out the equations then is deciding on a grid. What are you going to use for your X and your Y axis? And there really is no right or wrong, but there is a better, best, and worse one. And here's the hint I'm going to give anybody listening here is I find that the best coordinate system that works out the best is to have your x-axis, or y, it wouldn't really matter, but it's just kind of easy to say x-axis. Have your x-axis be the direction of the acceleration. Okay? And when you look at the equations, you'll begin to see why, because that means this equation right here just becomes ma. If you, again, set it up so that your x-axis is the acceleration, there is no component to the acceleration. And so we don't have like a cosine of an angle or sine of an angle in this part of the equation. But the real benefit comes on this equation, where then this would be 0, because all the acceleration is x, meaning none is in the y. And having this equation equal to 0 usually makes it much easier. So, like I said, you don't have to do this, but if you do, I think you'll end up with easier equations. So that's my recommendation. Now, of course, in order to do that, that means you might have to twist or redirect your x-axis into a non-traditional direction instead of just horizontal and, positive x's to the right. And that's what I'm going to end up doing here. I'm going to do this, and I'll do it in green and put it in my free body diagram. I'll say I'm going to call down the incline, because that's the direction of the acceleration, is x. And so that means perpendicular to that is the y. And so like I was just saying, it has a huge mathematical advantage and a disadvantage. There is a couple, but they're kind of minor. One Probably the biggest disadvantage is it's not something you're used to. It's not the traditional way. And because of that, maybe it takes a while to kind of really feel like this is a better option because it's just going to make you feel uncomfortable. Of course, the other thing is then, and you see it right here, once I twist my axes, the force of gravity is no longer along the y-axis. And if it was all along the y-axis, that would make easier way to deal with gravity. So now I've got components, and so that's kind of a bummer. However, I gained two advantages here where the frictional force is going to be opposite of the x-axis. So that'll be a negative x-axis. And the normal force is all along the y-axis. So that's a benefit too. So I would say those two benefits outweigh the loss of that one. And the biggest benefit of all is this right here. So I wouldn't even pay attention to your forces and which one has a more of a benefit. It really, the biggest benefit is when the x-axis is the full acceleration. That way you don't have to put like a cosine or sine here. And over here you can put a 0. All right, well, again, that would be my recommendation for this. Now, that being said, once you make that decision on your x-axis, you go ahead and just kind of look at your components. And here's where some experience is going to be gained. I'll just look at my three forces. I have friction, I have normal, and I have gravity, and I'll just do it in that order. And again, remembering I'm looking then at the components. And so right here, the force of friction, okay, is all in the negative x direction. So right here I would say negative force of friction. And just for completeness then, maybe I'll put a 0 for the amount of y component due to friction. All right, so there are my x and y components of friction. All the friction is in the negative x direction. None of it is in the y direction. And following that same logic, I'll go to the normal force. All right, so the normal force, all of it is in the y direction and none of it is in the x direction. Then go to the third force. This might be the harder one here, and that's because looking at it on a grid, and maybe I'll just kind of draw from this incline here a triangle. Remembering now this mg is the hypotenuse. And you might need to do a couple steps to convince yourself that that angle there is also theta. Maybe this is where step one with the physical picture can come back to. If you kind of draw a line that is perpendicular and a line that is straight down, that is this angle right here. And so if this angle is theta, this one in here is 90 minus theta, which, remembering this right here, is 90. So that means this one in here, the one in question, must be theta. So there it is. That's what I have then. I have that this angle is theta. And of course that's useful because I want to find the x and y components of my mg. So let's see. The y component would be adjacent to the angle. So adjacent uses cosine. So that means I would have mg cosine theta right here for the y component. And over here, I would have mg sine theta. That's this opposite one for the x component. So you can think of mg as made up of this much in the y direction. So mg cosine theta plus this much in the x direction. Now the other thing is we've got to decide what to put here. Do we put a positive or a negative? And if you look at this vector, it is down in the sense of a grid in the normal direction, or the traditional direction, but it would be down and then to the right. So as far as the x direction goes, it's in the positive direction. As far as the y direction goes, it's in the negative. And I probably shouldn't have done those in green. So there's positive, there's negative. All right. So by the way, there is the completion of step number 3. Okay. Step 1, good physical picture leads to a good free body diagram, which then leads to writing out the equation. And then the last one, not to make it sound so easy, but just solve it. And that's usually the easier of these 3 steps, because at this point it's just math, and you've been doing math probably a lot longer than you've been doing physics. Okay. Now, for this problem, I don't think we have to actually do all this work, because as I come back to the question just gives me the coefficient of friction and then says the kinetic friction acting on this block has a magnitude of. And so that's all they want is the friction. And so I didn't put it into this equation, but it's the coefficient of kinetic friction times the normal. And we could then solve for the amount of friction if we just knew the normal. And that we can get right here from the y direction. This says the normal would be equal to mg cosine theta. And by the way, just in passing, there's, I think, a human tendency to think that the normal force always comes out to be mg, and it does not. It does many times, but it does only if an object is either A, stationary and not not accelerating, and there aren't other forces involved. And usually there's something more going on, and so sometimes the normal force is equal to mg, and other times it is not. And this is a case where it is not. Okay. So to answer this question, I would just say then the force of friction is the coefficient of friction times the normal, which is mg cosine theta. And so now if I grab my calculator, I can go ahead and solve this. So the coefficient for this particular problem was 0.332 times the mass, 6.08, times g, and then times cosine of 30 degrees. And it looks like a 17.1 newtons would be the answer, which does look like it agrees with, the corrected answer, helping out this individual here. And this is the correct number. Now, it's not required, but it might be kind of nice then to find the acceleration. And so this was a little bigger problem or longer problem, this being the force of friction we just found, 17.1. This being the component of the force down the hill. Why don't I do that one? 6.08 times 9.8 times sine of 30, which is a half, gives me 29.8. The mass is 6.08, and I can get the acceleration. Now, again, I want to emphasize this was not required on the quiz, but it, could have been a very standard question. Find the acceleration. So you first would come over here and get the normal force, and then use that for friction, and then continue on what I'm doing now to get the acceleration. So I've got this already in my calculator. Let me subtract, and I'll just go up and copy and paste that one and hit enter. So that's what I get when I combine those two together. And then so if I divide it by 6.08, I get an acceleration of 2.08 meters per second squared. So this problem could have gone a little further, and hopefully if it did or did not, you still see it as the same type of problem where, again, good physical picture, free body diagram, write out the equations, and then solve. All right, well, I'll stop there and continue on with the next problem on another video. Hope that helps.